Plate tectonics. What happens when the continental plates collide? Which countries are most prone to earthquakes and volcanic eruptions? How is soil formed? Welcome to our channel. This course will teach you everything you need to know about the dynamic Earth from the inside out. You'll discover what makes the Earth quake, how plate tectonics work, and what geological time really means. So let's get started. Tectonic plates move around the globe. They are responsible for forming entire mountain ranges in just a few million years, but they also shape the face of the Earth over billions of years. As you already know, there are several types of plate boundaries where these massive slabs of rock meet. At divergent plate boundaries, tectonic plates move away from each other. This can happen when magma rises up and pushes the plates apart. For example, at the mid-Atlantic ridge, magma spills out between the Eurasian and African plates, creating new oceanic crust and pushing the plates apart. At convergent plate boundaries, plates collide with each other. If an oceanic plate collides with a continental plate, the denser oceanic plate will typically sink into the planet. This process is called subduction. Subduction zones are also associated with volcanoes because as the seafloor is dragged down, it melts and releases water and gases, which rise up and solidify into new igneous rock. When the continental plates collide, neither plate is subdued because both have roughly equal density. Instead, they buckle and fold, creating large mountain ranges like the Himalayas. And at transform boundaries, plates slide horizontally past one another. Most of the friction is released in the form of earthquakes. If you want to learn more about plate tectonics and other dynamic Earth processes, stay tuned. But before we continue, let's check your understanding with a quick knowledge check. Pause the video here if you want to make a prediction. Then click the link in the description to see how accurate your prediction was. Now let's go back to the video, erosion and weathering. Imagine you're standing in a canyon surrounded by towering rock walls. How did these formations come to be? What forces shaped them over time? Wind, rain, and ice slowly break down rocks and minerals through a process known as weathering. As rocks are exposed to the elements, they undergo physical and chemical changes that cause them to crack, crumble, and eventually turn into soil. Chemical weathering occurs when reactions between rocks and water, oxygen, or other substances cause the rocks to decompose. For instance, when acid rain falls on limestone, it weathers the rock more quickly than if it were exposed to rain without acids. Physical weathering, on the other hand, does not change the rock's chemical composition. Instead, it breaks down the rock without altering its mineral structure. One common type of physical weathering is frost wedging, which happens when water seeps into cracks in a rock, freezes and expands, putting pressure on the rock and eventually causing it to fracture. Another process that causes physical weathering is the growth of plant roots. Roots grow and expand, putting pressure on rocks and eventually causing them to crack. Over millions of years, erosion and weathering have created some of the world's most iconic landscapes, such as the Grand Canyon. In addition, they play a crucial role in shaping the Earth's surface by transporting and depositing sediments in new locations. For example, rivers carry sediments from higher elevations to lower elevations, eventually depositing them in valleys or deltas. Volcanic ash and dust can travel long distances through the air, eventually settling on the ground in areas far from the volcano. These processes of erosion and deposition continuously shape the Earth's surface, creating and destroying landforms over time. And it all starts with the breakdown of rocks and minerals through weathering. Volcanism. Imagine you re-hiking up a trail leading to the top of a mountain when suddenly the ground begins to shake beneath your feet. You look up to see molten lava and volcanic ash spewing out of a crater. You've just witnessed an eruption of a volcano. A volcano is formed when molten rock, known as magma, from deep within the Earth is pushed up and erupts through the crust. When this happens on land, it creates a cone-shaped structure that we recognize as a volcano. Volcanoes are often found along plate boundaries, particularly at convergent boundaries where two plates collide and one plate is subducted. As the seafloor is dragged down into the planet, it melts and releases gases and water vapor. These materials rise up toward the Earth's surface, and when they reach the crust, they can solidify into magma. Over time, this process can create chains of volcanoes. Eruptions occur when the pressure from the magma is greater than the weight of the overlying rock. The magma then forces its way to the surface, releasing tremendous energy in the form of heat and light. Volcanic eruptions can have both positive and negative effects on the environment. On the one hand, volcanoes can create new land and provide fertile soil for agriculture. On the other hand, eruptions can release harmful gases and ash into the atmosphere, which can damage crops and disrupt the climate system. Earthquakes. Did you know that our planet is constantly shaking and vibrating due to the movement of tectonic plates? Earthquakes are sudden and often violent tremors in the Earth's crust caused by the release of energy in the lithosphere. Most earthquakes occur along plate boundaries where the edges of tectonic plates meet. When plates collide or pull apart, stress builds up along the boundary. When the stress exceeds the strength of the rocks break and the energy is released in the form of seismic waves, causing the ground to shake. The point where the rocks break and the earthquake occurs is called the focus or hypocenter. The point on the Earth's surface directly above the focus is called the epicenter. Earthquakes can cause significant damage to buildings, infrastructure, and natural environments. Understanding seismic zones and conducting regular drills can help mitigate the impact of these events. In fact, knowing where earthquakes are most likely to occur helps engineers design structures that can withstand seismic activity. The San Andreas Fault in California is an infamous transform boundary where two plates slide past each other. It's one of the most seismically active areas in the world. Mineral resources. Minerals are natural substances with distinctive physical and chemical properties, composition, and atomic structure. They are used to make everyday items like smartphones, cars, and even jewelry. Some common examples include quartz, mica, calcite, and olivine. Many minerals are extracted from the earth through mining, while others are obtained from seawater or air. Sustainable use of mineral resources is essential to meet the growing demand for these materials while protecting the environment and conserving resources for future generations. It is important to consider the environmental impact of mining and extraction processes and to develop technologies that can reduce waste and pollution. The mining industry plays a crucial role in providing the raw materials needed to support various industries and drive economic growth. However, it also has the potential to cause significant environmental damage if not carried out responsibly. Techniques like strip mining and mountaintop removal mining can cause habitat destruction, soil erosion, and water pollution. Additionally, the extraction of some minerals, such as uranium for nuclear energy, can have long-lasting radioactive consequences. Sustainable mining practices aim to minimize the environmental impact of mineral extraction while providing a continuous supply of these valuable resources. Climate interactions, climate change, and geological processes are intricately connected in a complex feedback loop. Volcanic eruptions, for example, can have a profound impact on global temperatures. Large eruptions can inject massive amounts of sulfate aerosols into the stratosphere, which reflect sunlight and lead to a temporary cooling effect. Conversely, the warming climate is causing rising sea levels, which in turn accelerates erosion along coastlines. This process is further amplified by more frequent and intense storms that are associated with a warmer climate. Rising temperatures also affect the stability of permafrost, leading to the release of methane, a potent greenhouse gas. This creates a positive feedback loop that can accelerate climate change. Understanding the interplay between these processes is crucial for predicting future changes and developing effective mitigation strategies. In fact, by studying past climate shifts, geologists can provide insights into how current changes may unfold and help us better prepare for the challenges ahead. It divides the Earth's history into vast stretches of time, allowing scientists to study and comprehend the planet's evolution over billions of years. Geological time scale. The geological time scale is a system used by geologists to organize the Earth's history into different periods and eras. This time scale is divided into eons, which are subdivided into eras, periods, epochs, and ages. Each division represents a significant event or change in the Earth's history. For instance, the Cretaceous period, part of the larger Mesozoic era, marks the time when dinosaurs roamed the Earth. The Cenozoic era, which began about 66 million years ago, is the current age of mammals and humans. Understanding the geological time scale helps scientists interpret the vast array of rocks, fossils, and other evidence of past life on Earth. It provides a framework for organizing and understanding the planet's history and allows scientists to study the evolution of life and the Earth's environment over time. Natural hazards. Natural hazards are geological events that pose a threat to human life, property, and the environment. They can occur naturally and often pose significant risks to human activities. Volcanic eruptions, for example, can cause widespread destruction, while earthquakes can trigger tsunamis and landslides. Understanding the risks associated with these hazards is crucial for developing effective prevention and mitigation strategies. Communities located in seismically active zones or near volcanoes are particularly vulnerable to these natural phenomena. By studying the frequency and intensity of past events, geologists can help predict the likelihood of future occurrences and assist in planning for potential disasters. Conservation and sustainability. In recent years, there has been a growing emphasis on the conservation and sustainable use of natural resources. As the world's population grows and demand for resources increases, it's crucial to balance economic development with the need to protect the environment. This is particularly important in the field of geology, where the extraction of minerals and other natural resources can have a significant impact on the surrounding ecosystem. Sustainable mining practices, for example, aim to minimize the environmental impact of mineral extraction while providing a continuous supply of these valuable resources. Similarly, efforts are underway to reduce waste and pollution associated with oil and gas production. By adopting sustainable practices, geologists and other earth scientists can help ensure that natural resources are available for future generations while minimizing the negative impact on the environment. Research and technology. Technological advancements have revolutionized the field of geology, allowing scientists to study the Earth and its processes in greater detail than ever before. For example, geographic information systems (GIS) allow geologists to map and analyze spatial data, helping them identify areas at risk for natural hazards or mineral deposits. Remote sensing techniques such as satellite imagery enable the monitoring of changes in the Earth's surface over time, providing valuable insights into processes like erosion or volcanic activity. Drilling and sampling technologies allow scientists to collect data and materials from deep within the Earth, enabling them to study the planet's interior and reconstruct its history. These technological advancements have enabled geologists to make significant discoveries, develop new resources, and better understand the complexities of the Earth's systems. As technology continues to evolve, we can expect even more exciting developments in the field of geology in the future. Thank you for joining us on this journey through the dynamic Earth. We hope you've enjoyed learning about the amazing processes that shape our planet from the inside out. Remember, the Earth is a living, breathing system that is constantly changing and evolving. By understanding the forces that shape it, we can better appreciate the beauty and complexity of the world around us. Don't forget to stay curious and keep exploring the world. Who knows what amazing discoveries await us?